the optimum filter. In this section, we'll determine the filter transfer function for optimum bit error performance. In last case, we have considered integrate and dump filter, and we have determined the signal to noise ratio for this case and uh, the bit error rate for the integrate and dump filter. But this bit error rate may not be minimum or optimum. So in this section for the optimum filter, we'll determine the filter transfer function, and our input signals will be either xt, maybe either x1t or x2t. So input can be either x1t and x2t, which is a general input signals. It is not a or minus a, it is general x1t or x2t. And our noise will be a generalized Gaussian noise. It is not white noise, it will be generalized Gaussian noise. In previous case for integrate and dump filter, noise was white Gaussian noise, but in this case it will be generalized Gaussian noise. Now if without the presence of noise, if input is x1t, output will be x01 01t, and if input is x2t, output will be x02t. See here, after this output we have a sampler which will sample every t seconds. So y small t here will be y capital T, because output now dependent on the t, 2t, 3t, so time instance. So output can be expressed as yt equals x01t plus nt if input is x1t. For x2t input, output will be x02t plus nt. Now if we draw these outputs by some levels, if we assume that outputs having some levels, and that level is x02 and that may be x01, and here we are assuming that x1t greater than x2t and x01t greater than x02t. So based on this, you see x01t maybe have higher level and x02t having lower level. So I'll decide a decision boundary. Based on this, we'll decide whether the received signal is transmitted x1t or x2t. So decision boundary generally we take in the middle. So middle, this level is correspond to average of x1, x01 and x02. So this level will be x01 plus x02 by 2. And the difference between the decision boundary and the signals are, so this difference is x, so this one minus this one, x01 minus x01 plus x02 by 2, so that one minus x02 equals x01 minus x02 by 2. So that difference is x01 minus x02 by 2. Similarly, that difference will be this one minus this one, so it will be x01 by 2. Now consider the noise is Gaussian noise and this ANT part. So we have drawn this x01 and x02. Now consider the noise part. Consider that is the distribution of noise, probability density function of the noise. So we know the two parts. Now consider the case 1. Consider case 1. So in this case, assume x2 was transmitted. Assume x2 was transmitted. Assume x2 transmitted. Now if x2 transmitted means maybe this one, and if the noise is positive, if the noise is positive, if n0t is positive and it is added, so x2 was transmitted. As a result, your output will be x02. Output will be x02. x022. So x2 was transmitted. Output without noise is x02, and n0t is positive. So that can be seen from this diagram. x2 was transmitted. x2 was the without noise, and noise is positive. And see, if noise is greater than this difference, then the addition, this plus this noise component, this addition will be somewhere here. So if n0t, that is noise component, greater than this difference, that is greater than x01t minus x02t by 2. So if noise component is greater than this one, so this plus this noise component will give you value somewhere here. So in this case the yt will be in this region. Yt will be in this region. As a result, receiver will assume transmitted signal as x1t. So receiver will assume transmitted signal is x1t, and there will be some error. I repeat once again. I assume my voltage levels after the filtering without noise is x02 and x01. So if the yt is in this region, below this level, receiver will assume transmitted signal as x2, and if yt is in this region, receiver will assume transmitted signal as x1. So in this case, x2 was transmitted. So without noise, the filter output will be x02. Now if the noise is added, then x02 plus some n0t, and n0t is greater than this difference. So this summation x02 plus n0t will be here, will be in this region, and the receiver will decide in favor of x1t. So there will be some error, and that is correspond to, see, n0t greater than x01t minus x02t by 2. So that is correspond to this region. So that may be x01t minus x02t by 2. Why I am taking the positive side? Because I already assumed that x01 is greater than x02, so that's why this difference will be positive. And this inequality shows this region. So that is the region. So in this region, if x01, x2 was transmitted and noise is in this region, so then there will be error. So we need to find, that will be the probability, n0t greater than x01t minus x0 2t by 2. So that will be the probability, and that will be the probability of error. So we need to determine probability of error. Similarly, if I assume x1 was transmitted, x1 t transmitted, so output without noise will be x0 1t, and if the noise n0 t less than by 2, so that is correspond to this region. So in this section, that will be the probability of error for this case. So if the noise is this one, maintain this relationship, there will be some error.